So in summary, there are reactions that go forward and some reactions where the reverse occurs. And that's what you're looking for, is those double arrows right here. Now notice, you've seen this graph before, and I kind of mentioned equilibrium when I showed you this graph, but you didn't quite know what it was or what to do with the information. But here it is again, and you can see that you have reactants making products. This particular reaction goes forward only. As the NO2 is used, what is happening to NO and O2? You're gaining them. Now, according to what we learned in kinetics, what can we say about the relationship between the creation of NO and O2?
There's two NO per.
Yeah. So NO is made faster than O2. It's made faster by double. Okay? So that's what this graph would tell you if you were looking at it. No problem, thanks. And it really can't speak to how much NO is used. You can look at the coefficients. What is the relationship between the usage of NO2 and the creation of NO? They're made at the same rate. And as you saw in the video, where the water equilibrium starts not going in reverse, you can see that as the concentration of NO2 is being used, eventually the concentration evens out. Okay, so the concentration versus time is the same forever. So we're not changing the concentration as we reach equilibrium. We're only changing concentration as the reaction is attempting to reach equilibrium. Was it 12 or did I not update this with the new book yet? 14? Yes, sorry. Yeah, so I need to 14. Okay. Chapter 14. So I need to explain to you, K. Okay, so do you remember what K means? It's a rate constant, right? Now imagine if you were to add, and we haven't really spoken about equilibrium since the summer, but it's Le Chatelier's principle isn't too hard to remember. Essentially, if I take some more gaseous water and I add it into my equation, let's say this equation is at equilibrium, how would you expect adding water to disrupt the equilibrium? Okay, it changes the equilibrium, okay, and how might it change the equilibrium?
It would no longer be at equilibrium, it would change reactor until
Precisely. It will attempt to react more until that new gaseous water is used. So what we used to say in Le Chatelier's principle here during the summer was that adding water, gaseous water, pushes the equation to the right. Pushes the equation to the right. Now consider an equilibrium mixture in a closed vessel reacting according to this equation. What happens if you add H2?
It'll be pushed to the left.
So we would say that this equation will be pushed to the left. So we don't have to remember that, but here is the law of mass action. Okay, so that's actually the title of what we're going to be doing. We're going to be writing the law of mass action. Now, it was a little difficult in the kinetics chapter because some of you had a hard time remembering what I was asking for when I said write the rate law. I had all kinds of iterations that y'all made up, okay? But if you recall, or if you later realized that when I say what is the rate law, okay, I was asking for something like this, where you would note what x was and you would note what y was. But some of you plugged in for k, didn't need that. Some of you plugged in for r, didn't need that. The rate law was just an equation with these exponents included to show me the rate order of the reaction. Now, in this particular instance, I can give you an equation, and this here would be the law of mass action. Looks a little different. What did we add here to this particular equation? Yeah, so before, if you recall, the rate law equation was based mostly on just the reactants because we were talking about initial rate of reaction. Okay, but we're not talking about just the reactants now. We are talking about the reactants with relationship to the products. And when you talk about reactants with relationship to the products, we are talking about an equation that shows you a ratio. Now keep in mind, if we say that we have %40 of the class, or 0.4, are women in this class. I think it's more, but let's say 40%. Okay, and then we were to make a law and say, well, the constant is 40% of females will be in AP chemistry. What if we double the number of students, but the rate law constant held true? Would that change the percentage? No. You would maybe double each. So the good news this time, though, for K is that K is going to be unitless because of the ridiculousness of the situation, right? So K is unitless, and K is going to be a constant despite the concentrations, right? This is more of a constant with relationship to the amount of products versus the amount of reactants after equilibrium. Keep in mind, you got to say after equilibrium, okay? So, in this particular case, you're welcome, Alex. Coefficients are always the exponents when you're writing the law of mass action, okay? So the good news is no tests are needed. We don't need to divide anything. We don't need to graph anything. In the kinetics unit, the coefficients for the balanced equation were not necessarily the coefficients in the rate law for x and y. Here, plug it in, okay? So you got your 2. Woo, put the 2 there. Look at the 2, put the 2 there. And then this is a 1. Now, of course, how do we calculate K? We need some numbers. Yeah, and we'll definitely get some numbers. So I'll let you write this down. Oh, thank you for that very good question. Absolutely. Reactants always go on the bottom. It's products divided by reactants. Products divided by reactants. And you'll get used to that. We're going to practice that. So now K is going to tell you something. Whereas K before didn't really tell us much. K was just an arbitrary constant that we used to figure some stuff out in the Kinex unit. We found K, yay, we had a constant, and we can manipulate the equation in several ways, finding rate, finding concentration, etc. However, this K, when you find the K, will tell you something about the equation. So if you think about the math of the situation, if you've got products, well, divided by reactants, and I always want you to think about this. If your K is humongous, what can we say about the numerical comparison of the products to the reactants? In other words, what can we say about the amount of products versus the number of reactants? More products. See? Large K, more products. Simple. Yes? So far? And if you have a large K, as you can see in this graphical representation, more products are made. Most of the reactants have been converted to products. And then if you're at equilibrium, some go this way, and some go this way. But regardless, the amounts continue to stay like this. How about a small K? How about a very small K? What does that mean if something has a very small K? What can we say with relation to how it reacts? So, moving on from that argument. K always has the same value to given temperature regardless of how much you start with. Okay, so temperature will change K, but and watch for that. Obviously, you're not going to have problems in the very beginning that change temperature because it involves another equation. We got to learn how to do the basics before we start changing temperature. But if we keep it at the same temperature, no matter what you start off with, K always has the same value. We always go back to K. But if you think, go back to, let me make my example easier. 50% women, 50% men. Okay, that is 10%, or I'm sorry, 10 out of 20, or 20 out of 40, right? Or 40 out of 80. The percentage remains the same despite the number of individuals. And that's what we're trying to say in this slide, albeit maybe perhaps you don't understand the verbiage, but that's essentially what I'm saying. I'm saying for at a given temperature, there are a lot of different values that you can have, but K will certainly remain the same. That's the purpose for K. You can't change the K. And that's a trick question on the AP exam and my exams. We're going to say something about, if I change the concentration and I add more water, what will happen to K? Okay? And some of you might go scribbling all kinds of answers and doing some math, or you could just say, K stands for constant, brah. Okay? Constant, man. C-O-N-S-T-A-N. Done? Yeah. Equilibrium expression is the reciprocal for a reaction in reverse. So if you reverse the reaction, you turn the equation around. Okay. However, you need to call it K prime. Do you know what I mean by prime? K prime. Going to this paper here, let's see how far we got. Okay. Now, some of this is mixed in, but you can see that so far we have learned this part, which we're going to practice right now. Okay. And that's where you take the coefficients and the ingredients, so to speak, and place them into this expression. Okay. At some point, we're going to be talking about not the concentrations of products, because you can't describe a gas as having a concentration. You can describe a gas as having a pressure, and so the expression works the same for pressure. You can see there is a summary of the K conclusions that we can make. And it is also important to note that if you ever run into an ingredient that has a little S, or a pure liquid, what letter do we use for that? An L. Okay, because, well, solids and pure liquids like water don't actually have concentrations, right? You can't say the concentration of water. Concentration goes to explain how much stuff is in water or whatever other solvent that we have. At some point, we're going to learn how to convert. Don't worry about that yet. Here's what I started to talk about, 1 over K, K prime, K double prime, etc. Hess's law will go on to that. Okay, and this is where the fun starts, right here. Yes. And by fun, I mean some serious fun. Okay, the icebox. Determining how concentrations change equilibrium and calculating K. Woo! Exciting. Okay, so let's do some practice now. So let me point out a couple things on this worksheet. I'm only going to state the semi-obvious. Your instructions are here. For the following 3 reactions, that's the only challenge you need to get through. Is first is thinking about how you're going to write the expression, as I taught you, the expression, right? Then you may plug some stuff in, okay, kind of mentally. But first, state whether the equilibrium is product favored, reactant favored. How would you be able to know? Well, again, the values are expressed as concentration at equilibrium. Okay, we're not going to give you not equilibrium until we introduce icebox and torture. Okay, for now it's stating at equilibrium, and so you can actually look to see, oh well, how much NH3 is there at equilibrium, and then whether or not your K should be high or low. It's like a prediction, and then you just calculate your Q. Which is pretty math intensive, right? You've got this to the power, this to the power, multiplying and then dividing the other value to the power, you see? So practice getting fast at that too. So that's for the first 3 problems. And then let me know if you have any questions on the others. Now, we said that you can set up the law of mass action for equilibrium expressions involving pressure. And here you see an example of such an expression using pressure. Now, the thing about the pressures, and I don't know if you remember, partial pressure, but there's the law of partial pressures that state if you put 3 gases in a container with 3 different pressures, when you put them in that container, you will essentially add their pressures up. Okay? So you have 3 gases in 3 containers. You put them all into one of the original containers, and some of them are at 1 atmosphere, 3 atmospheres, and 4 atmospheres. The total pressure ends up being, do you know? Dalton's law of partial pressures? Hey, remember that law? No? Guess not. But anyway, so you add them up. That's just a review of. Remember we did the lab, hydrogen gas, the vapor pressure of water in the burette, and the supposed pressure of the hydrogen. And basically we had to find the vapor pressure of the water at a given temperature and pressure, and then subtract it. because partial pressures work just by adding, and you can subtract some out of there. But anyway, the important part of this slide, aside from that little review, would be this equation, which allows us to adjust our K for aqueous solutions, for example, and turn it into a K for pressure. So we can essentially go from Kc to Kp. The problem arises is that gases are particularly susceptible to temperature. And pressure is particularly susceptible to the number of moles in the container. You double the moles, you double the pressure. So, those are just factors we need to include when we convert Kc to Kp. The moles present and the temperature. Alright, so that wraps up the first side of this page here. The first problem set number 1.
What's R for this? Is it the same as when we did ideal basketball?
Yes, there's a specific R. You just have to look at the units that are involved. And so apparently that would be the point 0.08 what? 4? Oh, that's right. 0.0821, and then so if you recall, you've got your liters, your atmospheres, moles, and kelvins. Okay, so go finish the rest of that page before we go on to problem set 2. So the letter Q is used to determine if a reaction is at equilibrium yet. Now, what happens if you do calculate Q and Q is equal to K? What can we say? It's at equilibrium. What happens if Q is not equal to K? It's not at equilibrium. So hopefully we get them equal when we run Q, because then we don't have to do any work. However, if Q is not equal to K, we're not equilibrium, and certain things are implied there. Ready, spaghetti? So, again, now imagine, and this is where people kind of get mentally confuddled. If Q is greater than K, it has to shift to the left. Why in the world would Q be greater than K? Well, Q will be greater than K because the numbers at the top of a fraction, you know, where you have the concentration of, what goes on top? Reactants over products. Wait, did I say that wrong? This number starts getting higher if there are too many products. Just imagine an extreme situation when you have all products and very little reactants. So just go ahead and, you can give yourself like a pretend situation here. Okay, what's 100,000 divided by 1? Okay, so that's huge. And if your K is, 1,000, you overshot temporarily. The opposite is true. Okie dokie, roll. All right. Now we might be giving you K. Okay? So, let me start over. You have a situation where you have K. Now, when you're given K, you know something special is going to happen. Okay? Now, before we were calculating K based on the concentrations of reactants and products. Okay? If we're given K, we probably have to determine the concentration of products and reactants backwards. Yes? So here's the idea about how we're going to manage the situation. Now, you are all the best class I've seen at following protocol, and it is absolutely essential, some of us, that we absolutely learn the protocol for this lesson. Absolutely learn the protocol exactly as being demonstrated to you at this time. Okay, we call it ICE. ICE, baby. To go. Okay. So, it's called ICE for a reason, but let's just say, all right, let me take this down to simple times. You got 8 molecules and 6 molecules. Okay, that's what you're starting with. You see? That's called initial concentration. Yes? The question is, what are they at equilibrium? So you have to go from what you have to what you will have by using that K, because K will tell you, right? K tells you how far you go until your equation is done. And we're going to use this ICE method for all the other chapters. So it goes like this, the easy part, right? You thought that was all that we were doing was finding K? No. All right, so you write the law of mass action. All of these are candidates for being in the law of mass action. They're all gases. Can't get away with eliminating any of them. However, we're going to get so far into ice, you're going to forget the whole solids and liquids thing. Okay? And that's where I'm going to get you. Because we're going to be deep into ice boxes, and you're going to be making ice box after ice box after ice box, and all of a sudden, boom, that S will come back.
Yeah.
And you're going to throw it into the law of mass action and get the wrong answer.
Yeah.
And of course, it's double deduction, because not only do you get a deduction for the wrong answer, but for throwing S into the law of mass action. The solid, you know? It's sad times ahead. Okay. Okay. So we're going to ice that problem. Ice it. Uh-oh. You mean I got to draw boxes? Yup. Yeah, you do. Okay. It's actually quite simple when you get the hang of it. Try not to freak out. Here are those words again. Initial, change, equilibrium. This is our money right here. We want the answer. Okay, but we can't have it yet. So let's do some plug it in, plug it in. You with me so far?
Yes.
Initial, what we started with, and of course, since we haven't done the reaction yet, we have no products. Now here's the good news. What's Q? Quick, quick, like a bunny. 0 divided by whatever 8 times 6 is.
0.
But whatever, Q is 0, right? Q is less than 2, because K is 2. Anyway, my point is since we have no products yet, we don't have to calculate Q, because we know we have to go in the forward direction. It's a whole lot of information at once, right? So we don't need Q, because we already know it's going to go forward. Q doesn't need to tell us that. okay, because it hasn't gone forward at all. So forget the Q for now. We're going to assume we need to go forward. We have not reached equilibrium because we have no products. Oh man, that's a whole lot of unknowns. You're welcome. I'm going to say the scariest thing to you you've ever heard in about 5 minutes. Okay. You just wait. It's like a horror movie. Everyone scream. All right. So, the change when we're going towards equilibrium is going to be negative some amount, right? Oh no, the secret is being revealed. Negative some amount. And of course, since it's a 1-to-1 ratio, it's negative the same amount from the other reactant, right? I mean, you lose a molecule of H2O, you lose a molecule of CO. They go together. Okay? So we'll tell you what happens later if there's actually a coefficient in there. Ugh. Okay. And then of course what we lose here, we gain here and here. So equilibrium is conveniently written as 8 minus something, 6 minus something, and then that something will be made. Literally, what is 0 plus x?
X.
Literally, what is 6 minus x?
6 minus.
So you're just using some basic arithmetic there to get to the equilibrium part. Yeah. So there's the bottom line. Okay, just rewritten. You don't have to write that again. But you have to solve for x. The good news is, we can probably guess what x is in my example. Right? Or can we? Hold on, write that down real quick.
Well, it can't be 8 or 6.
That's right. Math boy over here. Can't be 8 or 6. Can't be 8 or 6, right? Okay. Through trial and error, you could say, well, x is equal to 4. But what if we don't know the answer by looking at it? We have 2 fun things for you. The preview to the awfulness, which is your favorite term. Okay? And of course, once we do FOIL that, we've got an x squared and an x and
Fun.
a quadratic equation.
Miss Miller.
Okay, see, some of you felt that, didn't you? Okay, you're supposed to scream, but whatever.
Oh, sorry. We're different.
Jumping out of this though.
Huh?